Hey, good evening all. So we can start the class after 5 minutes. We can wait for some times and then we can start. We can wait for 3-4 minutes. After that we can start. Okay, I think we can start now. So good evening all. So this is the Electrochemical Technology in Pollution Control, the NPTEL online certificate course. The course instructor is Professor Kemudakavi. So I am Shivankar Mandal from Indian Institute of Science. So I am doing a PhD at Solid State and Structural Chemistry unit. So basically I used to work on electrochemistry, catalysis and energy storage system. So okay, whatever we have learned previous class, so after that what we'll discuss today, some titration technique, and I will summarize whatever we have learned previous class. Okay, So in the first class we have discussed about the introduction, and the second class we have discussed some solution properties. So today we'll discuss some electrochemical method. Okay. So whatever we have learned in the last class, the different type of concentration term like molarity, then mole fraction, ppm, all these things. And after that we have discussed La-Sutter's principle. So what is La-Sutter's principle? Tell that if you have some system which is in equilibrium, and if you disturb the system externally, then system try to minimize that disturbance. So basically if you pressurize the system, then the system try to respond in that way that it can minimize the external pressure. So after that we have discussed about the Henry's law, so then Raoult's law, Dalton's law. So all these things we have learned. So how the pressure of the total solution is depend only on the mole fraction of the solute, not the solvent. So that things we have learned. And then we have discussed different type of properties like vapor pressure and boiling point, then freezing point, all these things. So we have discussed that why the vapor pressure lowering in the case of solvent, and why the because if you have some container, and in the container you have the solution, so in the surface you have the solute particle also, not only the pure solvent. So that vapor pressure basically how much gaseous phase of the solvent is there in top of this solution. So if you have on the top there is so much solute particle which is not vaporized, then the amount of the solvent particle in top of the solution will decrease. So that's why the lowering the vapor pressure. Okay, so that things we have discussed in the previous class. Then after that we have discussed the osmotic pressure, that is pi is equal to CRT. So while C is the concentration of the solvent. So basically from there we get to know how the pressure of the solution is depend and which way it will go. So that osmotic pressure, osmolysis also we have discussed. And after that we have learned different type of acid based dissociation constant. So electrolyte dissociation, from there we get to know that kW, that is 10 to the minus 4 for water, and that is concentration of O plus and O is minus. So that is called this is called electrolyte dissociation constant. And then acid base also we know what is strong acid, what is weak acid. And after that buffer solution, how the represent the pH of a solution. If the pH is changing, then how it can be resist by the solution, and that is known as the buffer solution. So that things we already have learned. And along with that we have discussed the activity and activity coefficient, how the activity coefficient is related to the concentration. So that also we have discussed that activity A is equal to activity coefficient with multiplication by the concentration. So that things also we have discussed, an ionic product of water, so that I have written also here. And along with that we have discussed common ion effect. So if you have some common ion like acetate, sodium acetate and acetic acid, so if you add sodium acetate, so the equilibrium is shift in the left side of the solution. So that also we have discussed. And the solubility product, so we have discussed these things, so many example, and how the sparingly soluble salt, how we can measure the solubility of sparingly soluble salt and solubility product of the solution. So today also we will discuss something related to solubility product also, how the conductivity, from the conductivity data we can calculate the solubility product and solubility of the salt. So that things also today some part of the lecture we will discuss. Okay, so with that we can start today class. So today we will discuss a little bit more about the electrochemical technique. So first technique is electrogravimetry. So electrogravimetry, when the terms will come, gravimetry, that means some weight related thing it's representing. So gravimetry means you are depositing something in the electrode. So and after that you are measuring how much compound is deposited on the electrode surface. Suppose I have taken one beaker, okay, and in that beaker I have some electrolyte. Basically, whatever we have learned solutions. So solution basically solute plus solvent. So in the electrolyte basically is one type of solution where the your ion is there and your solvent molecule is there. Like suppose KNO3 solution. So you have the K plus and NO3 minus, that is the electrolyte, and solvent suppose water is there. So that is called electrolyte because electrolytic process is happening in the solution. So for this it is called the electrolyte. Okay, so it is clear. Then after that you have the electrolyte. This is electrolyte, and you dip two basically plate, and you are applying the potential. And due to the potential, suppose you have in the electrolyte you have the Fe2 plus or Fe3 plus, then Fe2 plus is going to Fe0, then it is plating on the electrode surface. So you have taken the weight of the before the experiment, and so weight of the, I can write weight of the iron, that is before experiment, weight of electrode, and after experiment weight of electrode. So if you subtract from the after experiment whatever electrode weight, and if you subtract before experiment what was the weight, so if you subtract that part, then you will get to know how much your what is called iron is deposited on your electrode surface. So that things you get to know from the electrogravimetric method. So before going to more details of the electrogravimetry, you should know some of the term that is called Faraday's law. So what is Faraday's law? I can say Faraday's law. Faraday, Faraday's law, two statement is there. One statement is how much amount will deposit on the electrode surface. So that is depend on the how much current you are passing through the electrode. Okay. So if that means the weight of the deposited compound, that is proportional to current passes through the sample, or through the electrode, I can say. So that is one statement. Other statement, what it is telling? So other statement, it is telling that thus if you apply the current, so the equivalent amount of current if you apply, then the what is called the amount of different substance, suppose it is depositing on the electrode surface, then the same quantity of the electricity are proportional to their chemical equivalent. So means if you have aluminum 3 plus and Fe2 plus, and if you apply one equivalent, what is called one equivalent amount of current, one equivalent current amount of current means one mole of compound deposited on the electrode surface. electrode substrate. Okay, so in the case of aluminum 3 plus 3 electron is required. So, and in the case of iron 2 electron is required. So that means in the two cases, you if you apply same amount of current, then suppose 10 calorie 10 coulomb of current you have applied, then not 10 coulomb of current, that is current unit is ampere, so 10 suppose 10 ampere current you have applied. So with 10 ampere of current, how much equivalent of aluminum and iron deposit, that depends on the equivalent weight of the compound, equivalent weight of the compound. Okay, so okay, that is there, and okay, some other terms also we have learned, that is called cell. What is cell? So basically, cell is basically this beaker. Suppose I am taking, so that is the cell where you have electrolyte, you have electrode. So that is called cell. And then we have learned two type of cell. That is one is voltaic galvanic cell. One is galvanic cell. Other one is electrolytic cell. Okay. So what is galvanic cell? So galvanic cell basically chemical energy transformed to electrical energy. That means suppose here some redox process is happening. Suppose Fe3 plus or Fe2 plus, it is going to Fe 3 plus and 1 electron, so that extra electron is going to the external circuit, so you are getting the what is called current from the system. So due to this chemical reaction, you are getting the current. So that kind of cell is called galvanic cell. And what is electrolytic cell? So electrolytic cell basically electrical energy convert to chemical energy. Okay. That means suppose you have something and you are applying the you are giving the electron from the external source to the system, and due to that some chemical reaction is happening. So that means you are giving the electrical energy, due to that some chemical reaction is happening. So that means that is called the electrolytic cell. So this is kind of what is called term which we know already. So and after that we get to know that some conductance value, so equivalent conductance and then specific conductance. So there is some relationship we learn, that is called what is called equivalent conductance. What is equivalent conductance? What is the relationship of equivalent conductance and specific conductance? Can anyone tell? One can unmute or one can write in the chat box. So equivalent conductance, basically the specific conductance into into volume of solution in cc which contain 1 gram equivalent of solute or electrolyte. So that things we have represent that lambda is equal to k into v. So that also you know. Now question, and from there we get to know these key things we have discussed. So basically how the conductance or equivalent conductance will change for a strong electrolyte. that is KCl, which is we already discussed what is a strong electrolyte, which completely dissociate. So strong electrolyte, that is completely dissociate. Okay, so KCl means KCl, what it will dissociate? It will K plus and Cl minus, it will, so it will completely dissociate in the electrolyte. So, and in the case of weak electrolyte, there is acetic acid which will not completely dissociate. I think write it like this. So it will be equilibrium with CH3 C minus plus H plus. Now we will get this kind of what is called graph. But now question, this kind of graph, why in the case of strong electrolyte it is linearly increasing, and in the case of weak electrolyte, when the concentration is decreasing, so because square root of Kc, so when the concentration is decreasing, it is initially it is slowly increasing, after that it is strongly or rapidly increasing. Now question, why these two case it is different? Anyone can tell why it is happening like this? So the question is, anyone can unmute and can tell why this is happening. Strong electrolyte with dilution lambda increase linearly, weak electrolyte with dilution after some time increase rapidly. Why? This is the question. So can anyone tell why this is happening? Can unmute and you can tell. It is quite easy. So in the case of
Sir, on increasing the dilution number of ions remaining in the cell.
just a minute, my yeah, now you can tell. I think some issue was there. Yeah, someone is telling something. Yeah, it was right only. Can you repeat? Jayasriyan?
Sir, yes, sir. Sir, on increasing the dilution number of ions remaining in the same.
I don't know why it is echoing. Yeah, it is okay. Just a minute. Yeah. Can you tell again? Yeah, increase when the dilution is happening, number of ion is increasing. Something you are telling.
Sir, yes, sir.
Okay. So means you are telling for weak electrolyte or strong electrolyte?
Strong electrolyte.
Okay, so but in the case of strong electrolyte, if you because it is fully dissociated. Suppose I have taken 100 number of KCl, so it will produce 100 number of K plus and 100 number of Cl minus. So it means the number of what is called uh, ion is constant, no? So means because in strong electrolyte is fully dissociated, so the number of ion is constant. But in the case of weak electrolyte, yeah, it's true that if you dilute the solution, then whatever undissociate CH3 acetic acid molecule is there, that will dissociate. But in the case of strong electrolyte, what is there? It is completely dissociated. So means the number of ion is constant. So that is not correct. So basically means if you increase strong electrolyte, if you increase the dilution, that means you initially you have strong what is called KCl, K plus and Cl minus is there, and it is hydrated. This is also hydrated, so there is a some interaction between the K plus and Cl minus is there. So due to that, there is a movement of the K plus and Cl minus is low. So for this, initially the conductivity is it is called, it is here. When you are increasing the dilution, then K plus and Cl minus, there is distance is increased, so the interaction or electrostatic interaction between positive and negative ion is decreasing, so that they can move fast. So for this, it is increasing linearly. But in the case of weak electrolyte, what is happening? Whatever you told, that is correct for weak electrolyte. So for weak electrolyte, initially whatever CH3 COO minus is there and H plus, when you increase the dilution, whatever undissociated acetic acid is there, that will dissociate. As a result, your number of ion is increasing. So in the case of weak electrolyte, weak electrolyte with dilution, number of ion increasing. So number of ion increasing, that is one factor. Along with that, same strategy, that with the in between positive and negative ion, the electrostatic interaction is decreasing, so they can move fast. So for this, it is rapidly what is called increasing. So if dissociation is happening, then it may be not rapidly increase, it may be some kind of this kind of behavior it will observe. But with this case, in the weak electrolyte case, two factor is happening. One is number of what is called ion increasing, as well as the electrostatic interaction, that is also decreasing, so that it can move fast. Okay, so this is one key problem. So other problem is here we also equivalent conductance of ion at infinite dilution. There is given the what is called table. So from there we get to know that what is the conductance value. So that things we get to know. Here we can see that from H plus to lithium, sodium, potassium and ammonium plus, the conductivity is increasing. Now question, why it is increasing? Why it is increasing? Can anyone tell why it is increasing? Why in the case of lithium plus the conductivity is low? Because if you see, so the lithium sodium, it is in the same column. So as you know that if it is called one lithium plus, which is smaller size, so it can move fast because smaller size cation or ion can move fast compared to sodium and calcium. The ion size is increasing, so it can difficult to go from one side to another side. But still, here you can see it is the opposite trend. Why it is happening? Can anyone tell? There is another factor is there, means in aqueous solution when you will do, I can tell the thing. So that lithium which is smaller is ion, that means smaller in ion means the charge density is high. Charge density high. So if charge density high, so it will highly hydrated. So lithium means whatever is there, it will highly hydrated with water molecule. So when it is highly hydrated, the size of the lithium ion, that is hydrated lithium ion, that is quite bigger compared to sodium which is hydrated. That means hydrated sodium ion size is smaller than hydrated lithium ion. So for this the conductivity is increasing from lithium to sodium or sodium to potassium. And ammonia also, it is almost comparable with the potassium ion. It is clear? So we can go to the next slide. So next slide, what is called different type of cell is there, where we can calculate the conductivity of the electrolyte. So I am not going to more details about the what is called in the cell parameter, but what I want to tell, that is the how to calculate the cell constant, because you have the cell, and you can get this cell from the what is called market, and that things you can get. But after getting the cell, you have to calculate the cell constant, or you can make the conductivity cell also from the engineer workshop, and after that you have to calculate the cell constant. Suppose I have a cell like this, and I have one electrode here, it is connected one, and another electrode is like this. Okay, and it is connected with the what is called amperometer or some potentiostat. And your electrolyte you can put here, and you can measure the conductivity. But as we know, what is the relationship Ohm's law, we know R is equal to vi, sorry, V is equal to IR, and from there we know R is equal to rho L by A. What is R? R is the resistance. And what is rho? Specific resistance. And this is L is the length between these two electrode. This is the L, and this area of the electrode, that is A. Okay, so this A and L by A, this ratio is called cell constant. And what is the conductance? Oh, sorry. So conductance G usually people used to present, that is inversion of R. And specific conductance lambda people used to 1 by rho. Okay, so this is clear. Now if you want to know the conductance value or specific conductance of your electrolyte, then you get to know if you know the R value, then you get to know this value. this it is called conductance value, because G you get to know from the R value. But to get to know R, you can do the experiment and you will get the R value from the instrument. But if you know the R, but you have to know the what is called L by A, that is cell constant. So to calculate the cell constant, what is the procedure? Because people will not give the cell constant for a particular electrochemical cell, or it can be changed with temperature as well as in instrumechanical force also. So for this, when you will do the measurement, or if you want to calculate some conductance value of unknown electrolyte, then before that you have to what is called calibrate, or have to know the cell constant. So for that, what people have used to do, that some known solution like KCl, the value conductivity value of KCl is in the literature it is reported. So different concentration like 0.101 molar, or 0.02 molar, or 0.505 molar. So different concentration of what is called different concentration of KCl solution. They used to measure the resistance or conductance value, and in the literature it is given what is the conductance value of 0.1 molar of KCl solution. Then you will get to know one graph where you get to know from the experiment, you get to know the R value. This R value you know, and you know the specific conductance or rho, that value you know from the literature, because it is given in the literature for 0.01 molar of KCl at 25 degrees Celsius. What is the conductivity value? Then if you plot this R, or specific conductance, this specific conductance versus R. So concentration you know, and at specific conductance you know, and from the what is called experiment you will get to know the R value, and this rho value you will get from the what is called literature. Then different concentration you get like this. Okay, and from there you will fit the data in linearly, and you will get the slope. So basically that slope will give the cell constant. Slope is equal to cell constant. Okay, then for known concentration you get to know the cell constant for your electrochemical cell. And now you put your unknown K solution, or suppose you make KNO3 solution at 1 molar, then you put that solution here, and then you measure the what is called resistance value. So in unknown solution you know the R value, you know the L value, L by A value, cell constant from the earlier calibration, and then you get to know the rho value. So from rho value you get to know the specific conductance. So this way you can measure the conductivity of your electrolyte or unknown electrolyte. Okay, so that things I want to know here. Now question, if I know this what is called conductivity of this solution, then what is the application of this conductivity value? Okay, so this key application of conductivity conductance measurement, there is different type of application we can know, like first application we seen that applications what is called basicity and acidity of organic acid. So basicity measurement of organic acid. So one application we get to know, and other things is what is called solubility of sparing salt solution. Second is solubility. We'll discuss some problems on solubility also, because in some net or gate exam people used to give the question from here. sparingly soluble salt. So these things we get to know from this equation. Then ionic conductivity also we can get from this conductivity measurement. And what is called before that another the solubility problem we can discuss. Before that from solubility product lambda, this it is called specific conductance, and the equivalent conductance we already discussed earlier also, that is lambda is equal to k into v I have written. So v in cc I have written, I think earlier 2 3 class, and one equivalent of what is called compound is dissolve. I think these things I have written earlier also in the conductivity slide. So here you can write this V, you can replace K into 1000 by C, where C represent the solubility. C represent the solubility. Okay. So that things we can discuss little bit more when we will discuss the in problems. Okay, it will be more clear. So before going to that, we can discuss things that is called Colora's law. So what is tell this Colora's law? So this is applicable for infinite dilution. So infinite dilution electrolyte. So infinite dilution electrolyte. So what Colora's tell, that in any solution or electrolyte, per se electrolyte, it will be more clear. Electrolyte, the total conductivity or specific conductivity is the sum of specific conductivity of cation and anion. So if you represent in what is called equation, I can write lambda at infinite dilution, that is sum of the cation plus sum of the anion. So people used to write lambda minus plus lambda plus. Okay. So this is the Colora's law. But now question, it is applicable for what is called infinite dilution. Why it is not applicable in what is called concentrated electrolyte or medium concentrated electrolyte? Anyone can tell why it is not applicable for concentrated electrolyte? This Colora's law. Okay, I can tell. So because if what it is telling, that total electrolyte solution conductivity, it is the sum of the anion conductivity and cation conductivity. But if you see in the solution, as I have also discussed these things in the, I think, previous problem, that in cation and what is called cation and anion, so there is some interaction is there. So due to the interaction, electrostatic interaction, and what is called due hydrolysis is there. So due to the electrostatic interaction, there whatever conductivity value there is due to this electrostatic interaction, it will be lower. But in infinite dilution, it is like a gaseous state kind of thing, means there is no such interaction in cation and anion. So A plus, which is hydrated, and A minus, which is hydrohydrated, so that is means quite far to each other, so there is no interaction to ion in the solution, so that they can move freely inside the solution. As a result, whatever conductivity you will get, that is sum over cation conductivity plus anion conductivity. So we can discuss some problem, I think. Yeah, so we can discuss this problem, then it will be more clear, and how which type of question is to come from this. Okay, so there is written that earlier, whatever we are discussing solubility product calculation we already have done. Okay, so there they have given the what is called concentration, all these things. Here there is different type of what is called reaction, and you have to calculate. So means from the conductivity key value, how we can measure the solubility product. Okay, we can read the question. So calculate the solubility product of sparingly soluble salt calcium fluoride from the following data. So they have given some data. The molar ionic conductivity at infinite dilution. When it is written infinite dilution, that means Colora's law you have to think. Okay. So infinite dilution, calcium 2 plus and fluorine minus ion are given. So basically lambda calcium 2 plus. Okay, I don't know why it is. So calcium 2 plus. Okay. Keep. Okay. So calcium 2 plus, the conductivity value has given. What are the value they have given? We can write this one, or I can write the first what is called, what are the question is given. So lambda plus they have given. Okay, respectively the specific conductance of the saturated solution of calcium fluoride at room temperature is this, and specific conductance of water used for preparing the solution is 2 into 10 to the minus 4 Siemens. Okay, so that things they have given. Then we have to calculate the solubility product. So what are the things they have given, we have to think, and along with that they have given 4 options, which one will be correct, so we have to calculate. Okay, I think question is clear. So basically they have given the conductivity value. From there we have to calculate the specific conductance, sorry, solubility product. So before going to that, so what are the information is required that we can see. Okay, so as solubility product, they want to know what we know, calcium 2 plus when it will dissociate plus 2 F minus. Suppose initially it is 1, that time it is not dissociate, that is 0. So after dissociation or after dissolving the solution, some amount of what is called it is dissolved in the solution. So suppose the dissolve concentration is C. So 1 minus C is unreacted and this one is C is dissolved. Okay, and if this is C, then 2C it will be for fluorine ion, because 2 fluorine ion is there. Then what we know that solubility product is of calcium fluoride, that is concentration of calcium 2 plus into fluorine minus, that we know. Okay, I think these things we discussed in the previous class. Then what will be, you can write C, this is C into this is 2C square, so 4C cube, is it? Now we have to know the C, the molar concentration of the ion. So what we know, how to calculate the molar concentration C from the conductivity value, what we have to go. So this just now I have written, no, the molar what is called conductance of sparingly soluble salt, that is Ka by C. That we know. That means if you know the infinite, this is the infinite resolution specific conductance of calcium fluoride. So that things uh, if you know this part, and this K is the equivalent conductance, so that if you know, then C we can get to know. Okay, so I can write this one in such a way: C is equal to K by lambda 0. So what is lambda 0 from the Colora's law? Lambda of calcium 2 plus lambda of fluorine minus. Okay, that we know Colora's law. So in the case of calcium fluoride, what it will be? 2 fluorine minus is there, so it will be 2. Now this value and this value, it is given in the question. So in the question, what is it is given for calcium? For calcium, it is 104 into 10 to the power 4, and for fluorine, it is 48 into 10 to the power minus 4 Siemens meter square per mole. So for calcium, 104 into 10 to the minus 4 plus 2 into fluorine. 1 fluorine molecule, how much it is given? 48 into 10 to the minus 4. Unit is Siemens meter square mole inverse. How much it will be? Can anyone calculate? I don't have calculator, so anyone can calculate how much it will be. I can do in plus 48 into 2. What it will be? It is 96, I think. Okay. It is 96 into 10 to the power minus 4 Siemens meter square mole inverse. You people can do with me also in the notebook. Somewhere I may do the mistake, so that will be 2 into 10 to the minus 2 Siemens meter square mole inverse. Okay, so lambda naught, that things we know, but K we have to calculate. What is K? K is the specific conductance of calcium fluoride. So as it is sparingly soluble, so what is the specific conductance? You can write specific conductance. I can change the color, I think it will be good. Conductance of calcium fluoride, that will be what it will be? K of solution, because it is written there calcium fluoride specific conductance it is given. So and specific conductance of water, whatever that is given. So if you subtract that value, then whatever soluble electrolyte is there, that conductivity you will get. Okay, so K of solution minus K of water, specific conductance of water. So these two value it is given. Solution conductance what is there? 4.25 into 10 to the power minus 3 Siemens mole inverse, no, meter inverse. And for water it is given 2 into 10 to the power minus 4 Siemens into meter inverse. So you can subtract that to 4.25 into 10 to the minus 3 minus 2 into 10 to the minus 4 Siemens into meter inverse. What it will be? How much? And this will be, I can write this one. This thing Okay, I can rewrite this thing 10 to the minus 3 minus 2 into 10 to the minus 4. What I can write 0.2 into 10 to the minus 3. That it will be easy to subtract. So it will be 4.05 into 10 to the minus 3 Siemens meter inverse. Okay, so now you can put here and you can get the C value. So C is equal to K 4.05 0.5 into 10 to the minus 3 Siemens meter inverse divided by this value 2 into 0.10 to minus 2 Siemens meter inverse meter square. I think this is meter, I think, and mole inverse. So mole it will be go up, so it will be, what is the value? What is the C value it will come? Can anyone tell? If you divide these two, how much it will be? It will be 2.025 into 10 to the minus 4 mole. It will go up, so this meter square, that will be decimeter cube. Okay, so we know the C. Then conduct is called we have to calculate the solubility product, so that we know that is, what is this, 4C cube. So KSP, that is 4C cube, then 4 into 2.025 into 10 to the minus 4 mole decimeter cube, that whole cube. So this will be how much? Anyone can calculate? How much it will be? Answer, it will be mole cube decimeter 10 to the minus 9. What will be the answer? You can write in the chat box also. You people can do yourself, and after that you can write. So I will come. You people can write this thing, calculate how much it is. It will be 3.32 into 10 to the minus 11. Okay, so this is the answer. So if you see here, this is the C, answer C. Okay, so means what are the information they have given, so depend on that you have to calculate what you have to calculate. First you look at that, then whatever parameter is required, that we have to calculate whatever information they have given. So depend on that we have to apply different kind of equation like Colora's equation or whatever they have given. Okay, so we can discuss another question. Calculate the lambda naught specific conductance at equivalent what is called infinite dilution of calcium chloride. they have given calcium chloride and chlorine, the what is called specific conductance. So this is basically we have to use which law? Can anyone tell which law we have to use? Hmm? Colora's law. So according to Colora's law, what we know? According to Colora's law, lambda of calcium chloride, that will be lambda of calcium 2 plus 2 lambda of Cl minus. Okay, then they have given all the value 119.07 per centimeter square mole inverse plus 2 into this one 76.3 centimeter square mole inverse. So you can calculate this thing easily. 119 plus 6 2 152 Siemens mole inverse. Okay, now you can sum these two. 0.6 7 2 7 centimeter square mole inverse. Okay, so that value we have to calculate, so that things it is given. So it is quite easy. So next things we can discuss. So this kind of question usually it is to come in what is called in exam or net, all this key exam. So it is given that from the given molar conductivities at infinite dilution, calculate infinite molar conductivity for ammonium hydroxide. So what they have given? What they have given? They have given different compound what is called conductivity value, but you have to calculate from there the conductivity value of ammonium hydroxide. So how we can get this value? So we can first see what are the things they have given. So according to Colora's law, we have to think in that way. Okay, so if you write for first question for barium hydroxide, so what it will be? Lambda of barium plus 2 lambda of OH minus. It is given 457.6 ohm inverse centimeter square mole inverse. Okay, let's say this is equation 1. Equation 2, what the lambda of barium chloride plus 2 lambda of Cl minus. What is the value? 240.6 ohm inverse centimeter square mole inverse. So basically somewhere it is given Siemens. So basically Siemens is the this value okay, what is called inverse of ohm, so that it's called Siemens. So that is the unit of conductivity. Okay, so somewhere it is given Siemens, somewhere ohm inverse, so no need to confuse, that is basically the same thing. Okay, so third one, it is given lambda NH4Cl, that is lambda NH4 plus lambda of Cl minus, and that is 129.8 ohm inverse centimeter square mole inverse. So this thing is given, so we have to combine or subtract these three equations, and you have to make this one. So basically if I write what we have to make, that lambda of NH4OH, that is lambda of NH4 plus lambda of OH minus. So that these things we have to make from these three equations. So here you can see that number 3 there is NH4 plus is there, but Cl minus we don't need want. So Cl minus I can see that in this equation 2 there is Cl minus is there, so which I want to subtract. So that means if I subtract from here to here, there is 2, then I have to multiply this one as a 2, or I can divide this one okay, divided by 2. So I can divide by 2 this 2, then it will be Cl minus. So if I subtract this one, then Cl minus it will be subtract. But when Cl minus it will subtract, here also minus BH4 2 plus Ba2 plus it will come, then that also I have to what is called remove. As it is, it will come to minus, then I have to sum that one. So here you can see equation number 1, there is O is minus is there, and barium things is there. So basically what I can write, so equation I can do one by one, then it will be more clear. Okay, so means you can see this in equation number 1, O is minus is there, which we need. Okay, that means if I write 1 and 3, if you sum, then this part it will come, but extra barium plus it will come. So I can do one thing, I can do that equation number 3 plus half of equation number 1. I can do this way. Then what it will be? Lambda NH4Cl plus lambda barium hydroxide. So no need to write in the left side. I think only if you write in the left side, then it will be more clear. So if I do plus 3 half of plus 2, then what it will be? Plus 3 means lambda NH4 plus lambda of Cl minus. Okay, this is equation 1 right side, and plus half of left side lambda barium 2 plus 2 lambda OH minus. Okay, these things. So what it will be? Lambda NH4 Cl minus half of lambda barium plus 2 plus, and it will be plus because I am doing the summation lambda OH minus. Okay, so these things is came. Now I have extra this part, so I have to remove that one. Then you can see here is extra, these things is there, and also this chlorine also the extra. So here you can see in both case chlorine is there, so I think equation 2 we can subtract. So what is called minus half of equation 2, then what it will be? Lambda of NH4 plus plus lambda Cl minus plus half of lambda barium 2 plus lambda of OH minus this one lambda of half of lambda barium 2 plus 2 lambda Cl minus. Okay, then lambda NH4 plus these things and these things will be cut out, and these things will be cut out, so it will be only lambda OH minus. Okay, so this is your lambda NH4 plus OH. So these things we have get, that means whatever we have did, so that I can write now that equation 3 plus equation half of equation 1 minus half of equation 2. That things we have done. So for equation 1, 2, 3, they have given the value, so that according to that we have to do. So equation 3, what is the value? Equation 3, this is the value 129.8 plus equation 1, what is the value? Equation 1, 447, 457.6, that will be divided by 2 minus equation 2, 4, 0.6 divided by 2. And what is the unit? Ohm inverse centimeter square mole inverse. Okay, so what it will be? 298.8 plus it will be 3 2 2 2 8 plus 0.3. How much it will be? If people can calculate this one, how much it will be? Total 238.3 ohm inverse centimeter square mole inverse. Okay, so this is the answer. So this type of problem also used to come in the exam, so you can do this way to handle this type of question. Okay, so means this kind of equation 2 3 equation they will give, and from there you have to calculate the how much conductivity of a unknown solution, or from so you have to what is called combine or subtract 2 3 equation, and you will get to know the conductivity of the electrolyte. Okay, I think this thing is clear. Now we will see the ionic conductivity, ionic product of water. I think these things already we have discussed, so just I am going to that. So ionic conductivity product of water, that means what is called ionic product H2O, that will dissociate H plus OH minus. Okay, so that means according to Colora's law, what it will be? Lambda of H plus lambda of OH minus. And what is the ionic product? So it is means Colora's law, it is to say that the conductivity of the water, that will be combination of H plus and OH minus. Okay, so this equivalent conductance at infinite dilution for water, we used to write K alpha C into 100,000. If you know this conductivity of the H plus and OH minus, then you can get to know the conductivity of the water. And from there, for dissociation constant of degree of hydrolysis, we can say degree of hydrolysis, hydrolysis, that is alpha. So alpha, whatever we have discussed, so for acetic acid or something, weak acid, basically what I have written that time, suppose acetic acid, it will dissociate CH3C double O minus plus H plus. Suppose initially it is 1 and it is not dissociate, and after dissociation, suppose alpha amount of acetic acid is dissociated, then 1 minus alpha is undissociated, so this will be alpha and alpha. So we get to know that Kh, dissociation constant, that is C alpha into C alpha divided by C into 1 minus alpha, and this alpha, it will be C alpha square 1 minus alpha, and this alpha degree of dissociation, that is the ratio of what is called equivalent conductance of some equivalent conductance at a given dilution or given volume divided by infinite dilution conductance. So from, if you know the conductivity value, or it is given the conductivity value, then you can calculate KH. Okay, whatever way we have calculate solubility product, so that kind of problem also it is to come for it is called ionic product of water or any acid. So in that case, you have to calculate a degree of dissociation. If you know the alpha at infinite and alpha at a particular dilution, then you can get to know the alpha value, degree of dissociation, and you can put here in this equation, and from there you can get the Kh value. Okay, so this is clear. Now we'll discuss some of the conductivity titration technique. Okay, so conductometric titration, basically what we can get to know from conductometric titration, basically means whatever we will do acid base titration or that kind of thing, what we used to do, we used to put some indicator, and you will take the base in the it is called conical flask, and from the burette you used to add the acid, and you will titrate the molecule. When the equivalent point will come, that there should be some color change will be there. So from there you get to know that how much base or acid is required to neutralize that acid. Okay, so that is the thing. But in the case of conductometric titration, this is similar kind of thing, where we are basically measuring the conductivity of the solution. So basically you have taken, suppose, some acid in the beaker. Suppose you have taken some acid in the beaker, and you are adding some base. Suppose this is acid and this is some base, and in there you have a electrode, and you are measuring the conductivity of the solution. So from there, how the conductivity is changing, and with the adding of base. So from there you get to know when there is some sharp change in the conductivity value. From there you can get to know the what is called equivalent point of acid base neutralization. So what is the advantage of this? So in what is called the indicator, when you use, sometimes you get to know that okay, it is called purple color to fade yellow or blue color it will be. But sometimes we will not exactly know that when it should be deep purple color or deep blue color. So there some error can become in the in the this it is called colorimetric titration, or when you are using some indicator. But in this case, you can get more accurate value because you will plot the conductivity value, and from there you can get the what is called equivalent point of acid base. Okay, so that is the thing. So we will discuss some of the example when the acid base titration is to happen via conductometric titration, how it is with the graph. Okay, so this is one of the example. So they are this is which type of acid base titration? Can anyone guess? This is strong acid strong base titration, or this is weak acid weak base titration, or which kind of titration curve? Can anyone tell? So this is one type of example. Yeah, someone written. Yeah, Rao has written strong acid strong base. Yeah, that is correct. This is strong acid versus strong base. Okay, so basically here if you see that HCl plus you have taken in the beaker, or you have taken in the conical flask, that whatever I have given here. So this is so Nagaraju has written I have some work. It's okay, Naga, you can go ahead. So you have adding a NaOH, what it will be? Na plus plus Cl minus and plus H2. It is forming like this. Now my question, why this curve is like this? Means initially it is high, so means you are doing the titration, and here it is decreasing, and after sometimes it is going to a minimum conductance value, and after that again it is linearly increasing. Okay, and from here whatever value, that is the equivalent point. So that is okay. Now my question is, why it is the curve nature is like this? Other type of graph it is. So this is I can write, then this is the strong acid versus weak base titration curve. So here it is taking ammonium. So suppose HCl, you have taken HCl plus ammonium hydroxide. Okay, what it is going? NH4 plus plus Cl minus plus H2. Now question, one case it is sharply coming, and then after that it is increasing, and another case it is decreasing, and after equivalent point it is become the straight line. Okay, it is not so much changes in the conductivity. Now question is, why this kind of difference? Can anyone tell? They can you can unmute and tell what is the reason.
Sir, in the
Sir, in
first
the
case,
first case,
strong acid,
strong acid,
initially
initially the
highly mobile
highly mobile
replaced with
replaced with
less
less
ions.
ions. Mm-hmm.
Subsequent is
Point is
obtained. After
after
the
the
and the conductance is increases
conductance
sharply
is increases
the
sharply, the
presence of
presence of
sodium hydroxide
sodium
present.
hydroxide. Mm-hmm.
Again, when we
Again,
compare,
when we compare,
OH minus is having
OH
the,
minus is having the. Mm-hmm.
but in the second
But in the
case,
second case,
initially the
initially the conductance
lastly
lastly because
uh, to the highly
to the
replaced,
highly replaced,
and after the
and
equivalence,
after the equivalence,
conductance remains the
conductance
same as
remains the same as
the weak
the weak
is the
is
will
the
be
will be
sensation partially.
sensation partially. Mm-hmm. Yeah, you are correct. So Yeah, that is correct. Good. Thank you. So basically means whatever he has told, I just recollect this. So means HCl and NaOH. So basically whatever is initially it's yes sir.
I'm having one.
I am not able to hear you.
I'm having one doubt.
Yeah, tell me.
Um, uh, the previous lecturers, can we get the handouts like a presentation?
Yeah, I used to share the handout means whatever I am presenting here.
Yeah, okay.
This PPT, whatever, I used to share with the NPTEL committee. So,
Okay, no, actually, talk about Professor Mudakavi's presentations and
I am
because
not.
previously I took some NPTEL courses,
Mhm.
but NPTEL courses they will share that handouts.
Okay, handouts means whatever this PPT, all these things you want.
Yeah, exactly. PPT.
Okay, PPT, all these things I used to share. They did not share the Google Drive link.
No, no, this not shared.
Okay, okay. Okay, then I can share the Google Drive link in this group only. So
Okay.
from
And
there,
also, a sincere request is uh, can you share previous assignments, questions and answers,
yeah,
questions? So I will practice actually.
yeah, sure. Means whatever assignment question, usually I used to discuss in this discussion meeting. Okay.
Okay.
Along with that, I can share the assignment problem, whatever is there previous year and related to that. And also, I add some more extra problems so that some topic will be more clear. Okay. So that things I will share this PPT, all these things. I think some people access that whatever I have shared in Google Drive. Some Google Sheet is there. Okay, some Excel sheet. I think maybe they have shared that thing, so you can check your mail or somewhere it will be.
Sure, sure. Okay, sir.
Okay. Otherwise, I can share in the what is called in the this group also. I can share the Google Drive link, so you can get this PPT.
Sure. Okay, thanks.
Hmm? Okay. So basically, whatever he has told. So basically, whatever I initially we have HCl. So means in the solution H plus and Cl minus is there. So H plus and Cl minus as it is there. So we know that H plus conductivity is quite high. Okay, so this conductivity I think from the table I can get therefore 98.8. So this is the conductivity of H plus and this is Cl minus. So this is Cl minus conductivity is 76.35. Okay, so this is the equivalent conductance of these two. So that as H plus initially is there, the conductivity is quite high. For this it is quite high. After that, when you are adding NaOH, so OH minus conductivity, that is around 190 8.6. So if you don't know these things also, just remember that OH minus conductivity is lower than the H plus and equivalent conductivity conductance. Okay, so in the addition of NaOH, what is happening? Water is forming and Na plus and Cl minus is forming. Okay, so that means when adding the what is called NaOH in your electrolyte or in your solution, the responding conductivity ion is Na plus, Cl minus and H2O. And initial state, this whatever HCl is there, so that is also there. For this initial linearly it is decreasing. At the equivalent point, what is happening? At the equivalent point, all the H plus is converting to H2O and Na plus and Cl minus. So for this at that point your conductivity is quite low. After equivalent point, what is happening? After equivalent point, Na plus and OH minus, you are adding excess, so that in the solution Na plus is excess amount plus OH minus and Cl minus plus H2O is there. So this conducting, this Na plus and OH minus concentration is increasing. So for this again it is linearly increasing. So it is clear. Now in the case whatever in the case Rao whatever he has told, so in the case of weak electrolyte, so you have NH4OH minus, so H plus and Cl minus is there. So as initial state H plus and Cl minus is there, the conductivity is high. When NH4OH you are adding, so H2O, it is for H2O water is forming, and NH4 plus and Cl minus is there, and the conductivity of NH4 plus is quite low compared to Na plus and what is called uh, sorry, the NH4 plus its conductivity is quite compared to high compared to Na plus, because I have discussed that why Na plus or lithium plus conductivity is low compared to potassium plus and NH4 plus, because it is smaller size and the hydration cell is quite bigger, so the movement is low. Okay, so at you are using NH4 plus is adding, so it is decreasing. Okay, after that, as it is a weak base, so it is sparingly soluble or weakly dissociate. So for this it is not so much changing in the conductivity value. I think Mr. Rao also have told this thing, so it is the same thing I am telling. Okay, so another problem is the, I think I have written here. Okay, so I can't little bit shift this one, keep this thing, I can try keep here, or I can keep copy and paste. Okay, okay, so now question, this is one example of what, this is the weak acid and strong base. So this is weak acid and strong base, this is the example. Now why this is the this kind of nature is there? Anyone tell why this is this kind of behavior? We can
Sir,
give the
this is an example for mixture of a strong acid versus a strong base.
mixture of
Mixture of strong acid plus acid against strong base.
yeah, strong acid and strong base. Yeah, that also there this kind of behavior is to come, but this is a strong weak acid. Suppose CH3OH plus strong acid strong base. This is that example. It is to come like this. Because in the weak acid, what is there? So this is the weak acid and strong acid and weak acid mixture. Yeah, strong acid and weak acid mixture. Yeah, you are right. So what is happening here? Can tell anyone? Let's say it's Cl. It will be Cl minus here. So basically strong acid, what is happening in the strong acid, whatever we have observed, so it is with linearly it is in decreasing with NaOH because of the it is called H plus is consuming. After that what is happening, that acetic acid is there, which is a weak acid. When you are adding NaOH, what is it will dissociate, and CH3 C minus it is forming, plus H2O plus Na plus it is forming. So in the solution now it is these things is producing. So as Na plus is there, so for this slowly it is increasing. Okay, and after that when this is fully neutralized, you are again Na plus and OH minus is excess amount you are giving, so that it is increasing quite high. Okay, so these things is I think clear.
Yes, sir,
Yes,
it's
sir,
clear.
it's clear. Okay, so I think we can go to some of the other problem. Means this kind of precipitation reaction also there, and then redox reaction also there. So I am not talking about that thing. Uh, I'll talk some of the potentiometry or galvanostatic cell. So that kind of part I'll cover. Okay, because these all are similar type of thing. Okay, so let's discuss about galvanic or electrochemical cell. I think these things, Professor Mudakavi also discussed. So I just wrap up the things quickly so that whatever assignment question or whatever problem we will discuss, that will be more clear. Okay, so this is a galvanic cell. So what is there? You are taking some two beaker. So in the one beaker, what is there? One copper sulfate solution is there, and in the copper sulfate solution, one copper electrode you have dipped, and other one a silver nitrate solution you have taken, and you are giving the silver nitrate solution, a silver electrode in deep in the solution, and these two electrode or compartment, it is connected with some salt bridge. It is called salt bridge. Salt bridge basically it is maintaining the charge between the two beaker. Okay, so I will tell these things, cathode anode all these things will come. So I am not going to that part. Slowly we can go to that part. Okay, so this what is called solve is basically how we can make in the lab also. Basically you can take that gelatin, what is called some agar agar powder or gelatin powder, which is a kind of I can take polymer kind of thing. So with that you can take the KCl solution, so that you have the K plus and Cl minus, which can charge balance between two K electrode, and these two electrode you can connect with the voltmeter. So whatever the difference between these two compartment, that will show in the voltmeter how much volt it is, and this volt difference is depend on the standard potential of the reduction and oxidation of the it is called ion. So in the case of copper 2 plus, how much copper 2 plus to copper it is going, so whatever potential, suppose it is E1, and for Ag silver nitrate, so basically Ag plus it is going to Ag naught. Okay, so that is suppose E2. So basically it will give the information E2 minus E1. So whatever difference that is, that will give the in voltmeter. Okay, so that is there. So copper ion basically when you will dip in the copper plus copper electrode in the solution, what will be? So in the copper is going to copper 2 plus, and copper 2 plus it will go to the copper naught. Okay, so there will be in the electrode electrolyte interface, there should be some equilibrium will maintain. Okay, and in the in other case Ag plus, so it will go to Ag, and from the electrode Ag is going to Ag plus. So that kind of equilibrium it will be maintained. Okay, so now these things is there. After that we will discuss some of the parameters when this equilibrium or electrode electrolyte interface equilibrium is happening. So how it is happening? Okay, so there is some term is there like electrical double layer. So what is electrical double layer? So electrical double layer, basically suppose we have a deep one electrode which is positively charged. As you know, positive charge is there, then whatever negative charge is there in the electrolyte, that will come closer to the electrode surface, and it is what is called form two opposite charge or opposite charge separated by the electrode surface. So this surface is called double layer. Why double layer? Because positive and negative is there, so double layer. And this is also called the capacitance, also people call. What is capacitance? Anyone know what is the capacitance? So capacitance, basically two opposite charges are separated by a insulator. Two opposite charge separated by a insulating layer. Okay, layer. Now question, in the electrode surface, that is not the insulating in nature because it can conduct the electron. Okay, so but we are telling that it is kind of a capacitive nature. So actually in the electrode surface whatever is there, so that is means people used to consider that as a kind of insulating layer, means what is called in pure capacitor it is not. So there is some deviation is there from the capacitive behavior. So people later on okay, there is some other name also they have given, that is called constant phase element also instead of capacitance. People use constant phase element. So all these thing is there. Okay, and also from here there is a some inner Helmholtz sphere also people call.
Sir, these concepts are, we know that.
Sorry.
These concepts we know that still. But can we have little bit of oriented sessions,
Sorry,
calculations,
sorry.
and all?
Oh, okay, okay. Okay, you are telling that these things we have discussed, so I think more problem, all these things you can discuss more.
Yeah, these are from uh, uh, Professor Mudakavi's present. Little bit of like
Okay.
and assignment and all those things.
Oh, okay, okay. No, actually, I used to prefer that, means if someone did not get the time to what is called to get the time to see the video, then we can just recap the things so that whatever we'll discuss in the assignment, then
No,
that can be more understandable. Okay.
in the free time, uh, they see video. But in the problem sessions, basically we will and
Oh,
assign.
okay. Oh, okay, okay. I got your point. Okay. So, okay, then I can skip this part little bit, and I can discuss the what is called assignment question. Okay.
Yes,
I
sir.
think
Thank you.
some of the question I have discussed and some of the question is remaining. So I think this is the previous year some question. So which of the following is not an electrochemical electroanalytical technique? Okay. So here you can see different type of electroanalytical technique. So potentiometry one is there. Second option is oscillometry. Third option is coulometry. Fourth option is gravimetry.
I think it is B or C. Yeah, anyone.
Oscillometry. Okay,
Oscillatory.
gravimetry. What is gravimetry? Basically, we are taking the weight. Basically, taking the weight. but there is no electric transfer or something. Okay, actually oscillometry, the name is little bit fancy, or we are not so familiar with the oscillometry. For this it is feeling that okay, maybe this is the thing, but actually if you know the gravimetry, whatever weighing balance, if you think, so that things is there, means in the gravimetry what you used to weighing balance, basically you have taken some chemicals or something and you have put it on the weighing balance, you are taking the weight. Okay, so in that case there is not a electroanalytical technique. In a electroanalytical technique means you are something, some chemical reaction or something you are doing, and due to that some electron transfer is to happen. Okay, electron transfer is to happen, and due to that you are getting some voltage or current. Okay, this is the what is called general idea or general rule for electroanalytical technique. If you see the potentiometric titration or voltammetry, anything, okay, in that case you are actually transferring or sweeping the potential or transferring the electron, and you are getting the redox response or getting the voltage. Okay, so but if you see the gravimetry, like thermal gravimetry is there, TGA, thermal gravimetry analysis. So you are basically heat the sample, and due to the heat, whatever, suppose compound is dissociating, due to that whatever changes in the weight that you are taking. So it is not a electrogravimetry, this is only gravimetry. So it is the answer is not B, it is D. What is oscillometry? Oscillometry is basically due to the change of the pressure. This is some what is called medical instrument, or also means electrical instrument. Also, electrician use this instrument. Means if your what is called, if you have some wire, and there is some disconnection in the wire, then if you use this oscillometer meter, then you will get the current response. So if there is a disconnection, then you will not get the response. So basically in the oscillometer also people use in the medical, like some pressure changes is happening, then current and voltage also change. So if you see some movie or some hospital also, where in the operation theater, where means the patient is dead or it is in alive, so in the skin there is to some dropping or sinusoidal wave function it is to show. So basically it is, you are taking the breathing and breathe out, so your air pressure is going to the instrument, and due to the change in the pressure there is showing the current or voltage response. Okay, so that is the due to the oscillometry key principle. Okay, so means there also this electroanalytic, that is also electroanalytic technique, and potentiometry, you know that this is electroanalytic technique, and coulometry also basically what is called charge basically used to measure, and potentiometry voltage used to measure. Okay, and this charge measurement. Okay, so means these three is there, but gravimetry basically you are taking the weight, but there is no electron transfer or anything is not happening. Okay, so that means the answer is gravimetry. So this not the answer. I can do like this. Okay. Okay, so next question is, in polarography, pilot ions method cannot account for matrix effect, dilution effects. What is called either dilution or matrix effect, and none of these. What will be the answer? Polarography pilot ions method. So this is the polarography apparatus. What is the polarography apparatus? So polarography, basically there is some mercury drop, CGME used to tell. CGME. What is CGME? Control growth mercury electrode. Okay. So basically, if you see the here the apparatus, so this is the electrolytic cell, okay, and you have a anode, and this is the mercury. So mercury can drop on the electrolyte, as mercury is conducting substrate, so it can drop in the electrolyte, and you are getting the it is connected with the what is called circuit or potentiometer, so that you can get the current response, and the connection is happening due through this. Okay, here the mercury is there, so it is one connection is the cathode, and there another is the anode. Okay, when the drop is happening, so there is a make the connection in between the electrolyte and the mercury, and that mercury, as it is conducting, so it is making the connection. Okay, so in polarography pilot method, the question is, in polarography pilot ions method cannot account for matrix effect. So matrix effect, what is the matrix effect? One is dilution effect, either matrix or it is called either dilution or matrix effect, and none of these. So matrix effect, basically what is that? So basically this what is called mercury is dropping in the electrode surface. So when the connection will what is called made, there will be current response. After that, what is called when the drop is not dropping in the solution, so there is a disconnection, then there is no response of current. Then again when the what is called when again the when the current will come, then again it will be come the current, and then when the disconnection is happen, then it will be come to the lower value, and then like this. So if you do it time, then it will be like this. So this is called the matrix, means different point you are getting the what is called current value, okay, as a particular time, like this. Or if you see the voltage also, it will be like this. Okay, so this kind of thing. So this is called the what is called matrix effect. So that things can be measured from the polarographic pilot ion method. Okay, but what is dilution effect? So dilution effect we cannot consider in this, because what is dilution effect? Basically you are dropping the mercury in the electrolyte solution. Due to that, your electrolyte concentration is changing, but that things how much it is changing in the what is called current value or voltage value, it is not shown. So that means the answer is the dilution effect. Okay, because matrix effect you can get, so C is not be the answer, none of this, that is not the answer. So the question answer is B. So the third question is Grant's plot anti-lock of Na by 2.303 RT versus reagent volume is used to determine what? The nature of the test solution, the slope of the test solution, the concentration of test solution, the pH of the test solution. What will be the answer? Hmm? Grant's plot.
No idea.
No idea. Okay, so grand spot anti-lock Na by RT versus reagent concentration. So if you see these things, Nernst equation we know no E is equal to E naught plus RT by NF 2.303 log of oxidant by log of reductant. Okay. So Grant's plot antilog means of these things. So if you see E minus E naught, and it will be NF by RT NF by RT 2.303. Okay, that will be log of oxidant by reduction. Hmm? So if you antilog, if you take it, then this will be E, then oxidant by reductant. Okay. Then what is called from here. So basically it is the Giants plot. So this is the things. So from here these things versus volume used in the determination. So reagent volume used. So basically how much in the titration technique or conductometric titration, how much volume you have taken. So that things what is called from here which things we can get to know. So nature of the test solution, like I can take one example that acid base titration you have done, no? So it will be like this. Suppose strong acid versus strong base. It will be like this. This is the conductance value and this is the volume of the NaOH. So from here this is the equivalent point. So from here what is this is the giant plots, Grant's plot. Because these things from here it will come. Okay, so from here it will come like this. So how means this is for redox process, but what is called grants, but I have written this is for acid base titration. Okay, so means from here what we get to know. From here can we tell that it is which type of nature of the solution. If you don't know that which kind, this is strong acid strong base or some redox reaction is happening or that thing, so we cannot tell from this graph that how is the nature of the test solution. So that things we cannot tell from this kind of graph. That means answer what is called A cannot be. Then the slope of the test solution, slope we cannot tell. Other thing is the concentration of the test solution. That thing we can tell because from the equivalent things, one concentration if you know, then other concentration how much you can tell from that this solution equivalent point. Okay, so that things you can tell, and the pH of the test solution pH it is called we cannot tell from here because H plus concentration, how much H plus concentration is there. So that things you cannot tell from the equivalent point. So answer is the C. So bleaching powder is the suitable for influent containing cyanide because no effluents containing cyanide because into a harmless gas is produced. Cyanogen is not released in alkali condition. The reaction can be carried out at room temperature and all of this. What will be the answer? Bleaching powder. What is the by the way, what is the chemical formula of bleaching powder? We have read in school time. Bleaching powder, calcium hypochlorite, no?
Okay.
Okay. Calcium hypochlorite, OCl2. That is the bleaching powder. So bleaching powder is suitable for effluent containing cyanide because basically cyanide is harmful in our body or for our body. So to effluents what is called cyanide, bleaching powder is used. Why you have to use bleaching powder? You can write this one. If I dissociate calcium 2 plus OCl2 OCl minus. So what is there? This calcium 2 plus is there, no?
Mm.
So if I don't know means anything, what is this thing exactly is happening? Okay, but if you know that the calcium 2 plus, which is a alkali earth material, no? Alkali earth metal. So means it is called N2 is harmless as gas is produced. So because cyanide means Cn minus, so all these things. So this bond is C11 to C111N. So this is quite strong. So it cannot be dissociate in the what is called normal condition. So that means it is difficult to produce the N2 here. Okay, so that means this cannot be the answer. Cyanide is not released in alkaline condition. Yeah, so calcium 2 plus is there, so it can coordinate with this cyanide minus so that it cannot release. It can make the compound with the calcium 2 plus. So I think B is the answer. Okay, the reaction can be carried out at room temperature. So basically, this bleaching powder, whatever we used to use for the okay, what is called for desanification, all these things. So and when it is to react with this cyano things, so some tear gas is to form. So what is the tear gas, what is called the chemical formula tear gas? Tear gas is chloropicrin. We have read all these things in school time. Chloropicrin, what is the formula?
Fluoroacid.
Fluoroacid. Trichloronitrate, chloropicrin. And other also some tearing gas also there, like okay, 2 nitro benzo okay, cyano I cyano something is there, so that is also means TR. So concentration of the test solution in an electrochemical cell can be determined by Green's plot, EMF, potential volume curve, all of these. What will be the answer?
EMF.
EMF. Huh? EMF, electromotive force. What is EMF? Electromotive force. Suppose you have beaker and you have some electrolyte solution. Let's say copper sulfate, okay? And you have dipped one, suppose 2 molar you have taken. You have dipped one electrode and you have dipped another electrode. And you put one voltmeter and you are measuring how much difference is the potential, that is called EMF. So you get suppose 3 volt. Then from this 3 volt, how you can get to know that how much concentration is there of the copper sulfate? Can you get to know? just now we have discussed this Grant's plot. We get
Yes.
to know the concentration of the electrolyte. So it is written Grant's plot. So you can get to know from here how the Grant's plot means. From the Grant's plot you get to know the concentration. EMF, basically this is the condition. So you cannot, you just get, sorry, you just get to know the voltage of the electrolyte, or means two electrode. Okay. So, and potential volume curve means how the potential is changing when you are adding the what is called acid base titration. Suppose you are adding the so NaOH in the acetic acid solution, and you are getting the voltage versus volume of NaOH, and you are getting like this. Okay, so from there means if you don't know how much concentration of acetic acid or NaOH, then you cannot tell that how much concentration is there of the test solution. Okay, so one concentration should be known. So from the volume, we cannot tell that. Okay, 10 ml of NaOH we have given. So due to that, we get this voltage curve, and from there you can get the concentration. We should know what is the concentration of NaOH. Okay, then we can tell that these things. But Grant's plot, we can tell. Okay. So the next question is, find the value of equilibrium constant at 25 degrees Celsius of the cell for the cell reaction for a following electrochemical cell. They have given a electrochemical cell, and these things I think it is not mentioned. This is the cell representation. Cell representation. Okay, so basically in the electrochemical cell, what is happening, that can be written in the in this way. Okay, so here copper is going to copper 2 plus, and whatever copper is solid, for this it is written is like this, and copper 2 plus it is in the aqueous solution, so it is given in 1 molar. I think these things we know in class school time. So, and this two arrow, what it is representing, that copper and copper 2 plus, these are in what is called different phase. Okay, or different phase or different compartment. So this is the equation, and there it is given that two reaction, the what is the potential it is given. Okay, then what is the find out the equilibrium constant k you have to calculate. How you can proceed? Hmm? So basically two cell reaction is given, no? This side it copper 2 plus Ag is going Ag, and copper is going. So here I want to mention that E always it should be in reduction state. So E naught it is given in reduction, that value, and E oxidation is given minus. So if you write in this equation in reduction process, then it what it will be? It is positive 0.518 volt. Okay, so what is the cell E naught cell? We have to calculate E naught cell, what is there, because they have given the equation. So E naught cell is equal to 0.0592 divided by n, sorry, into n log of k. So E cell is equal to this one. So if you see this equation, so Ag is going to Ag plus, and this one. So we have know that Er minus El, that is the cell reaction, 0.0592 into n log of k. So this is, you can write 0.799 minus 0.518, 0.0592 into, here the n is equal to 2, it is given, log of k. How much it will be? 1. This will be 8, 2. This is volt, 0.0592 into 2 log of k. So means from here you have to calculate the k. I think this is easy. This way you have to proceed. Okay. And the answer it will be C. 3.1 into 10 to the power 9. Because it is called positive value. Why I have? Because these two are almost same. But if you see, here is a positive, here also positive. So there is no chance to come negative. So this will be the answer. Okay. The difference between actual potential and the equilibrium potential is called, what is called? I think it is discussed in the video. Deposition potential, over voltage, under voltage, residual voltage. What will be the answer? It is called over voltage. Is it not? I think it is discussed in the video. So what is the over voltage? Basically, suppose means in practical point of view, if I tell, suppose one reaction is happening, so Fe3 plus is going to Fe2 plus. Okay, and for that its potential, suppose E naught 0.776 volt. Okay, that means the reaction should happen in the 0.776 volt. But when I am doing in practical, Fe2 plus is Fe3 plus, Fe2 plus is going to Fe3 plus, E is happening at 0.81 volt. Okay, that means it should come, how much it is extra potential it is taking, around 0.2 volt maybe. So this means extra voltage whatever, or extra energy whatever we are giving, that is called over voltage. Okay, so this is the thing. Then what is the potential of following cell? So zinc is, this is the cell presentation. Zinc is going zinc to plus, and copper to plus is going to copper. E cathode it is given, E anode is given. Then what will be? E cell it is written. Which one will be the answer? E cathode, E cell is equal to E cathode minus E not anode. It is given here. So you can put the value 0.34
1.1
minus 0.76. So 1.1 volt means answer C. An electrical double layer is option A, virtual entity with compressed positively charged ions and negatively charged ions, physically Option B is physically reality which can be determined experimentally. Option C is an imaginary region in electroplating. Option D is a practical region with varying thickness. Which one will be the answer?
Sir, it is
Sir,
a
it is
B.
a D. D.
B.
B.
Physical
Physical
reality.
reality which can be determined experimentally. Okay, actually, it is not the correct answer. It will be what is called option A, virtual entity with compressed positively region and negatively. I can show if you see
But it
the.
is a very question. It is a very difficult question.
Okay, just a minute. I will come to your point also. Hmm. Okay, keep here. So here you can see that this is the double layer. Okay, positive charge is there and negatively charge is there, which is closely contact to each other. So this is called double layer, no? And other is this one is inner Helmholtz-sphere. People also used to tell, and this is outer Helmholtz-sphere. So where the positive and negative charge are loosely bounded. So if you see inner Helmholtz sphere, there positive and negative charge which is closely bounded. Okay. And there how the potential is changed, that things I think they have he has discussed. So in the inner Helmholtz sphere it is linearly, and after that it is exponentially. But in electrochemical cell, if you see, this is 220 to 300 Armstrong, the length of the what is called double layer distance. So it is quite
So
difficult.
that is the thickness or the distance.
Sorry.
That is the
That is the
thickness of
thickness of
the layer
the layer
or
or
distance.
distance? That is the thickness of the whole layer.
Okay.
Okay. Mm. So that Armstrong level it is there. So that means it is quite difficult to measure. Okay, because we used to do in electrochemistry also. So we cannot what is called at the electrode electrolyte interface, how the ion is coming to the electrode surface, and what is the length of that electro and electrochemical double layer. That is quite difficult because that length can be changed with different type of electrolyte also. Suppose you have taken KNO3 and other you have taken KCl or NaCl, then that both case the ion are different, so the property will be different and the solvation sphere also different. So it's difficult to what is called calculate the distance. So that means it's physical reality to determine difficult, but there is some analytical tool also there, means some impedance or something is impedance spectroscopy is there. So from there you can feed the data and you can get the what is called value of how much distance of that electrical double layer. But physically means like tape, whatever way you used to measure the distance, that is quite difficult. Okay, so the answer A is the correct. So dropping Merkel electrode is used for gravimetry, calorimetry, potentiometry, polarography.
Polarography.
Polarography. Yeah, so polarography. I think all the question is that's all. So whatever is there, if you have any question you can ask.
Sir,
Sir,
please
please
uh, PDF
PDF
of
of
yes assignments so
assignments
that it
so
will be
it
helpful.
will. Yeah, yes, yes, sure. I'll share the PDF of the. But you can once you can check the that things. I think some Google sheet is have shared, because this video also I used to upload in the YouTube, and that YouTube link also shared to the student. Okay, so Otherwise means if you are not getting, then you can mail to PMRF, sorry, NPTEL coordinator. Okay.
Okay, sir.
Okay. So they might be help you. Otherwise I can share in this okay, group also, in the chat box section I can share the link, so you can access that link also. Okay, so that is no issue, but in general whatever means procedure, so I used to upload in the Google Drive, and this video in the YouTube, and that link I used to share with the NPTEL committee, and whatever attendance is there, so that attendance sheet also I used to share. So that things you can get.
Okay, thank you
Okay,
very much.
thank you. Okay, so I think here we can conclude this session. Have a good day. We can meet in next week in the same time.
Sir,
Okay.
I will send.
Sir, I
I
will
will send.
send. I will send.
Please send
Please
that
send that
assignment.
assignment. Oh, sure, sure. I can say send to you. I am writing my mail ID. Okay.
Yeah, I am
Yeah, I
having.
am having. Oh, you are having my mail ID. Then I can share you. You just send me one reminder mail. Okay.
Okay, sir.
Okay, sir. So I can send you. Hmm?
Okay, thank you
Okay,
very
thank
much.
you very much. Thank you. Thank you.
Okay, shall I
Okay,
leave
shall
now?
I leave now? Yes, sure. You can leave.
Okay, thank you,
Okay,
sir.
thank you. Thank you.